Hi everybody, my name is Afshin Majd. I have good afternoon or good morning depending on the time of the day that you listen to this and watch this webinar. I'm a principal power system engineer with EasyPower. I have done a few webinars in the past, all on the harmonics and basics of the harmonics and renewable energy system. The last webinar that I recorded, unfortunately, wasn't of a good quality voice, so I had to summarize it and put a shorter version of it on our website. And today I am planning to actually do a full webinar, hopefully on the harmonic renewable energy system topic. And then at the end, for the second half of it, I'm gonna talk about the updates of 2014 version of 519, IEEE 519. So more or less we all are familiar with IEEE 519. The latest release of 519 is 2014, which has quite a few updates. And again, second half of this presentation, I'll start talking about those updates and how they are gonna impact any harmonic study if you perform them. So I'll start with this presentation, which I have covered it before. I will go more in depth, and I spend some time on the areas that I didn't cover in the past. And once I'm done with this part, I'll jump immediately to the next presentation, which is going to be 519 updates. However, just depending on the time, if I don't cover that presentation fully, again, I will continue on. We will have more webinars on the same topic, and every time I try to kind of follow what I have covered in the past. That being said, obviously the topic is harmonics in renewable energy systems. I already introduced myself, and we go to the first slide here. We need to follow a few steps whenever we want to perform a harmonic study, and those few steps include data collection. Usually, as it comes from the name of this study, it's going to be a larger system. If it's going to be a larger system, you would need to collect the data on your utility. You will need to collect data on available equipment connected to that system. And again, because we focus this presentation on renewable plants, let's assume that there are a bunch of either photovoltaic cells or renewable or wind turbines connected to the system, to the grid, and we wanted to see how we can model them. First step would be collecting all the information on the grid side, including available short circuit, which is probably the first step for almost any other type of a study that you need to do. You need to start from your utility. You would need to have the X over R values for the Thevenin model. If you decide to model it as a Thevenin model, you will need to have an X over R value for that. If possible, a frequency scan into the network. It's not always possible, but if you can get this information from your utility, this is the best way to model your utility. If not, a good substitute would be instead of using a Thevenin model, you can actually go a few steps or few buses up. And instead of putting just one simple voltage source, you can actually use a few buses up there and model it as, let's say, a few other sources. You can do, instead of, because if you use a Thevenin model, it's going to be a simple voltage source plus a Thevenin impedance, versus if you do a one bus, two bus, and then a bunch of cables or transmission lines and then a Thevenin model, it gives a little bit more depth. It provides a little bit more information in terms of the behavior of that utility system, which you can do. If not, and if available at all, you can do a frequency scan into the system, which provides a complete spectrum for the frequency response of your utility. Basically, anything more than an aggregate model will help. And measurements at the point of connection for harmonics, if possible, to 50th. And you would see that this is, again, part of the second half of this presentation, that IEEE 519 2014 requires us to go only up to 15th harmonic. Anything beyond that basically really doesn't provide much information to us, and we technically shouldn't consider it, at least after these updates of 2014. we shouldn't consider it like a harmonic. It becomes more of a high frequency, maybe very high frequency, which goes into a different category of studies. So data required from the turbines. If these are photovoltaic cells, you would need inverter information, because photovoltaic, as you know, it generates DC voltage, and it definitely has to go through an inverter. So if you have an inverter, you will need to know the frequency and the harmonic output of the inverters. If this happens to be a turbine, then you will need to have a full spectrum of that turbine. They both come in data sheets. They both devices always have and include this information. The manufacturers include this information in their data sheet. So it's something that I would assume that is pretty easy to get if we perform this type of studies. If it's something else, let's say VFDs or other inverters or rectifiers or other type of power electronics, which is not again the focus of this presentation, but for those either measurements would be the best, or again data sheet from the manufacturers. One difficult, I would say, or maybe different point about the harmonic studies is that a lot of occasions you would get data sheets from the manufacturer which whose data are different from what you test and what you measure on the field, and you have to find a good approach, and you use the type of data which are more reliable. Obviously, if you do perform a test, your test results, to me and my opinion, are going to be a better reliable source, because when you do a test, you test it on your system somewhere that you're going to connect your turbines. But basically, regardless of what approach you use, just as a software manufacturer, we can accommodate those data. So you can have those data and input them in the turbine and perform the studies. So the mode of, you would need to know the mode of operation of the turbines. They can run delta or star regardless of manufacturer. Type of turbine, they can be type 1, 2, 3, 4, and I believe I went through the details of them in the past presentations. Just a quick note that type 4 becomes the most advanced type of wind turbines. Usually manufacturers should provide these test results. Harmonics results are usually based at different output power levels. If you just want to run one scenario, you would run a full power scenario. You can use the harmonics injection numbers at full load, which I mentioned already, or you can create different scenarios to perform harmonics at different power levels, which again mentioned it. We will run one example for renewable plant, and this I haven't changed it. I believe it's very close, if not exactly the same example that I ran for the power flow. So very much the type of webinars that I put and I create, if you just watch them and follow them from the first one or the oldest one to the newest one, very much you can just start learning about how to model the system, and from the power flow, then basics of the harmonics, and then applying the results of the harmonics. And eventually I'll probably have time, but in future, to talk about the design of the filter, impact of the excuse me, filter in your systems as well. So now, that being said, a plant which was discussed in previous webinars is analyzed for harmonic spectrum. A hand calculation method will be used to verify the EasyPower results. The formula for the hand calculation will be discussed and analyzed. I won't go into a whole lot of details because we have seen that before. The factors involved in approximation of the formula will be discussed. So now let's take a look at the EasyPower file. Here. This is, and let me just put this guy deactivated. So what you see here basically is a model that you will use for your, let's say, your power flow calculations. We put this model together. I spoke and analyzed the way that we can just create a file like this. It's not really a large file. Usually, as discussed before, you would be considering either FERC 661 rules or IEEE 1547 rules. Regardless, you would come up with some power factor requirements, voltage requirements, frequency requirements, and let's say you cover all of them in your power flow case without having any harmonic. When you go to harmonic system, that becomes the starting point of our presentation. That's where I have this file already, and I have all the machines which are connected to this bus, and I would say, okay, now I would like to use some harmonic sources, and in order to use the harmonic sources you have to use a VFD. So instead of a generator, I'm going to use a motor, a VFD, the same rating, so that I can input the harmonic values in the system in EasyPower. That being said, I come back here, looking at these numbers here. This, in fact, in order to get here, I will go and say, okay, I'm done with my power flow. So I have my power flow numbers. We covered them before, not interested. I go and I will say, okay, this guy, this guy, this guy, and this guy, and this one, I want to activate them. Then I will go say this generator, this one, this, and this. I don't need them anymore. So okay, what it means is that I'm done with my power flow. I'm going to focus on my harmonics. In case you're not clear why there is a cap bank here, just a quick note, quick summary review of what we did in the past. You will have a cap bank to meet the power factor requirements. So I have this cap bank here to meet my power factor requirements. Instead of this point, I put it at the collector point, collector system. Those of you who come from wind industry, you would know that this is representing the collector system, where the entire turbines and plant and everything, the currents and all the power is coming here. We collect them here, we pass them through a high step-up transformer, send them to the utility. That becomes the point of interconnection to the utility, which is here. This example is 138 kV. Now, we calculated this value before, so I have this cap bank here, and I'm gonna go back to my presentation. Here, a table which we created for power flow, for 100% voltage, for 90% voltage, and for 110% voltage. So we created this table. This table was based on PQ curve of the turbines, which again, I have to refer you guys to my previous webinars on the details of this table. But basically, these are different points for the turbine, and 0, 500, 500. So these are all different points, and you multiply this column basically by 5, and you would get this column. Because you have 5 of them, this is rated value, not measured value, but rated value of power at the collector system. What it means that we have 5 of these machines, and if we had a lossless system, a system without any loss, then we will have this much power at the collector system. Now that we have a system that has some losses and we have an efficiency, that's what I measure. This comes from EasyPower. This value comes from EasyPower. This is if for the case that if I didn't have any losses, I didn't have any cable P losses, I would have been able to generate 500. Now that I have the cables, I'm generating 492. This value is the value without the cap bank. This value is after addition of the cap bank, and obviously cap bank in this mode is off, so that these numbers are the same. Because if your system is already absorbing reactive power, you don't want to have a cap bank so that it beats the purpose. That in generating mode, whenever you are generating reactive power and you don't generate enough, then that's where you have to have a cap bank. And as you see, these numbers go up. But when the system starts absorbing reactive power, I turn the cap bank off, which means that these values are identical. The same thing for 90% voltage, the same thing for 110%. And we discussed the fact of the impact of voltage change, that if the utility voltage changes, there would be a slight change in the capability of the plant to meet the reactive power values. In other words, let's just look at the similar values here. For 100% voltage, if each turbine is generating the same amount of P and Q, this is how much Q I'm getting here, this is how much Q I'm getting here. As you see, voltage has gone down, and this value, voltage has gone down from 100% to 90%, and this value has gone up, and here it has gone up even further. So let me see, for 2428, 2403. So these, oh, okay, from with the voltage change, in fact, which makes sense. If when the voltage comes down, the plant generates less reactive power, even though all the turbines, every single turbine is generating the same reactive power. It's just the impact of reactive power. And we see that the voltage goes up, the same plant has more capability or can generate more reactive power, even though, again, it's the same type of turbine, it's the same amount of Q by the change of voltage. So if somebody adjusts the voltage of the utility, you would be able to extract more reactive power out of the same plant with the same turbines generating all the same value of Q. So it's an interesting fact, but not necessarily related to this webinar, something that we as power engineers know very well, that the reactive power and voltage and the magnitude of voltage are directly related. So when I change the magnitude of the voltage, you would see the plant generates different amount of reactive power. So eventually I have all these columns for all different voltage, with without the cap bank, with the cap bank, and cap bank off for these areas. All these areas cap banks are off, so these numbers are equal. This is just a review of what we did in the past. Then you would see that you don't need any. Now there is some power factor requirements, and for that power factor requirements, as you see, I created a column here. That column tells me how much reactive power I would need to generate, in fact. And here, as you see, a negative number, just to make the longest story short, negative number, which means that you already have some extra reactive power. Here you still have some extra, even though the number is coming down. And again, you have some extra reactive power, and this one is again some negative number, and here it becomes a positive number. That's where you don't meet the requirements, and that means that you would need to, in fact, place or add a cap bank of this size to your system. So these all have been covered in the past with details. So I'm just reviewing them here, that you would need to add this much cap bank to your system. The rest, we have no deficiency. If we did, that would have been, in fact, a deficiency in terms of reactive power, which means that we needed to calculate the size of a reactor, but there is no need for that. It's blank, which means that we meet there. When the plant starts absorbing reactive power, we have no deficiency, but the plant, when generates reactive power, there is a deficiency there. That's a cap bank of 1207.63, in fact, kVr. That's the size of that cap bank. And for a second, I'm gonna move this screen, look at the value of this guy, and you see the same exact value has been added here. That's the cap bank. If you ask why so step by step, we do the power flow. When we do the power flow, we come up with the size of the cap bank. There has to be a cap bank there. If there is a cap bank there, that means that there is a possibility, there is a likelihood of a resonance. We can just run it and see that there is a resonance. Not to mention that these guys are source of harmonics. We have to make sure that that resonance doesn't happen at any of these given harmonics here. So all the steps that we have to take here. Now, come back here, next slide. Harmonic spectrum of the turbine. It's 3, 5, 7. This is just random numbers I put here. It's just, for example, as an example, you can certainly get the real values from any manufacturer and put them in here. How do you do that in EasyPower? This is how you would do that in EasyPower. You would come here, as you say, you turn this guy off, put equivalent, the same size VFD, and then you double click on it. Then you go to harmonics and you start defining these values. You can change them. You can add, put different values, anything you want. But so, and once you have it for one of them, you can copy paste it for other VFDs as well. We again come back here. This is how you would put all the frequency harmonics there. Now let's take a quick look at these hand calculations, and I have no intention of going into the details of this hand calculation, but the good point is that the formulas are given here, and I go more or less into enough details so that you can derive the formula yourself, or it's available in most of the harmonic textbooks. If you couldn't find that, by all means, you can always get a hold of me, send me an email, give me a call, and I'll be happy to share the information or more data, or even prove it to you if you want to. But these are pretty well-known formulas that we use for short circuit current and harmonics. For short circuit current on the immediate secondary of any step down supply transformer, the maximum symmetrical short circuit current can be estimated. This is this formula. We know that if you have a transformer of, let's say, 100 kVA, 7% or 10%, 10% impedance, this is the voltage of the base kV, which would be, let's say, secondary of the transformer. That would be your current on the secondary. There is a hidden assumption here, which I didn't mention it. That's when this transformer is connected to an infinite bus or infinite utility, or otherwise that becomes the maximum available short circuit on the secondary of that transformer. Because I didn't mention anything of the utility here, that's very important to know that if you have a utility and it has an internal impedance, this value is going to come down. But if not, then that's maximum short circuit current that you're gonna get. So given transformer kVA rating, nameplate percentage, percent impedance, and secondary voltage base, the short circuit current on the low voltage side of the transformer in amp is this value. Now, going to basics of 519, perhaps you can find these equations in 519. I haven't got them from 519 standard. I have got them from other sources and my past experience, but anyhow, if it's not clear, just let me know. Send me a quick email and I'll be happy to help. So if you have your source, if you have a source of harmonic and you have a capacitor, you're likely to experience a resonance point, or your system might resonate at some point. How it happens, if you look at the modeling, this is my system impedance. This is my source of harmonic. So this is my source of harmonic going to this bus. So this is this guy, and this is here. And then I assume that ground and ground, so these and these are in parallel. It's basically just the equivalent circuit of what you see here. So R, X, XC. Now it becomes more clear that, well, yeah, there might be a chance that if at some frequency these two cancel each other out, and you would see a short here. So, but let's see, let's take a look. I go to the next slide. To analyze this network, we simply parallel the two impedances together. If XL and XC are equal, then X total goes to infinity. So what it means is that, let's take a look here. If these two guys are in parallel, it means that 1 over 1 XL minus 1 over XC, that's X total here, you see, and that becomes the seen impedance seen from this point. And for modeling section, we know that X equals 2 pi F L, or XLH equals XL multiplied by H. XC is 1 over 2 pi FC. XC is XC over H. If we put these two values equal, it's very important to note that why we don't have a resonance at fundamental frequency. It's very easy to answer, because there is no way that in a normal design these two guys are cancel each other out. The fact that you would see a resonance at higher frequency is that as the frequency goes up, this value goes up and this value comes down, because XC is 1 over 2 pi FC. You can see it here. So as the frequency goes up, this guy goes up, this guy comes down. So now you see, okay, there is a movement that these two guys start approaching each other, and once they meet, once they cross, that's where we experience a resonance. So XLH becomes XL multiplied by H, XCH becomes XC divided by H. If we set these two equations equal, we get this value. H is equal to square root of XC over XL. A more useful form of the last equation is this value, and I cut all the calculations from this point to the other point, but there is a mention to them in my previous presentations, as well as if you ask and you send email, I have it. I can just prove it. It's not really, you can find it in textbooks, you can find it in any reference that discusses the issues of the harmonics. But basically I just really don't want to focus a whole lot on the formulas, but as important and as familiar this formula is for us in short circuit calculation, the same for this formula in harmonics, which means that you will have, this is the harmonic order of resonance frequency. So that's where you experience a resonance. In other words, if you have a system like this and these are the values, if I come here, that becomes, and I have these values, I have to just plug them in here, and that gives me the order of the harmonic for the resonance point. So now let's continue. Putting it in hand calculation, actually I said that I skipped the from values. I in fact didn't. H is equal to this value. It comes from 2 slides prior to this. I divide both numerator by Z base, then they both become XC fundamental per unit, XL fundamental per unit. Z base is equal to this value, and just to let you know, this is a transformer. Let's assume that there is a transformer here. Let's just assume that there is a transformer impedance here. This is a transformer. Let's just put it this way, because I have everywhere I have used the transformer value. So then 3 times 1000 times this value, transformer rating. This is here. If you divide them, you're gonna get this value. And if you plug them in the formula, you're gonna get this value, this formula. So in other words, what you see here is just the proof of the formula that I was using. And you can spend more time. Now the formulas and everything is here, and then maybe do it once for yourself so that you learn it. Usually if you do it, it's easier to understand, but you know, this is just a step by step driving this formula. Now let's go back to EasyPower, run a frequency scan, see what the frequency scan looks to be, and actually shows to be 10.7 here. This is a screen capture of EasyPower, but I come here, I come to frequency, and these are good for my summation. They're gonna give me THD for the voltage, THD for the current. On the other side, again, THD for voltage. You can see different values. This is the VRSS, this is ISS, this is just addition of the magnitude of the voltages. So what it says that your equipment connected to this bus are going to be exposed to a voltage equal to 1.073 here. So this is for summation. These are really good for summation calculation. You can do anything here, but for resonance frequency, you would come back to your original file and try your original file. So what I'm going to do here is that I'm gonna choose this guy, choose this guy, choose this guy, this, and come back, deactivate this, and this, and activate, and come back here, run a frequency, here, run a frequency, and get a value which seems to be equal to, if you look at this side here, you will see the numbers, almost 10.6, 10.7. That's what we got before. So I'm gonna here, or actually in fact you can see the values from here, and close it, and go back to my presentation. So here the formula and hand calculation is going to give us 1 over 7% times 1.2 divided by 10, or almost 10.9. EasyPower gave us 10.7. We have to keep in mind that that formula is approximate. So EasyPower is a more reliable source. But I mean, the numbers are close enough because the system is not that complicated. Once the dimension and the dimension and size of the system goes up and the number of equipments add up, then it becomes more complicated. You perhaps won't be able to use that formula as easy as I did now, and you would rely more on software packages, obviously, like EasyPower, which the harmonic module, the harmonic focus is really strong. It's very well written, prepared, and covers almost every need that you might have for your study. So that being said, okay, let's take a look at the 7%, see where that 7% comes from. Here, impedance, you see 7%, and 1.2 would have to be the size of the transformer. And let's just go back just to make sure where these formulas come from. Let's take a look here. Cap, so that was 7%, cap bank kVR and transformer kVA rating. Okay, let's take a look. Okay, this guy is 1.2 and this guy is 10. Okay, now I go back to the formula again and let's take a look. 7%, size of the cap bank and size of the transformer. You do the calculation, you're going to get 10.9. There is a good correlation between the EasyPower results and hand calculation. There are approximations which makes the formula deliver different results from the EasyPower. We neglected the resistance of the source. Almost all the renewables are source of the harmonics injection, being photovoltaic, being wind generation, being any type of switching devices. They're gonna introduce a lot of harmonics, and this number of these devices actually is going up as we do more renewables. We build more renewable plants. There is going to be more harmonics issues, and there has to be more solutions, and we need to have a better knowledge. So all these things together means that you and us, basically, we have to add to the features of the EasyPower, obviously depending on the feedback of our customers. But for now, it actually covers almost every need that you might need. And I just wanted to use one application in an area that you might think it is sometimes challenging. I actually used it to evaluate some, let's say, IEEE 1547 or FERC 661 requirements here. So that's one application. You can come up with a million different other applications. It's just one idea, one example that I wanted to show here. The system has to be checked for the resonance frequency. The dominant frequency in the system should be away from the resonance. Due to the existence of the cap banks, we can tune it to filter out unwanted frequencies. So that very much concludes this presentation here. And let me just do a quick, I don't have a whole lot of time left, but let me just go and quickly talk about the 519 2014 updates. Again, my name is Afshin Majd, and I'll be happy to help. If you have questions, just call me up or send me an email, and I really encourage you to, if you have the harmonic module, to just perform the studies. If you don't, talk to our technical support department and our sales department, and if you just get the version to help you with the projects. If you guys, if you do a lot of renewables or any type of a study that requires harmonic work. And one good reference for harmonics is 519, which is the topic of my next presentation. So what I do here is that I'm gonna close this one and go to my folders and grab the 519 presentation. So that's here. So now let's just quickly go over these presentations here. And I have 519, 9092, and 2014 both open here so that we can actually look at the examples together. So IEEE 519 2014 updates changes versus 519 1992. First, field measurement equipment. There are quite a few new statistical methods introduced in 2014 version which are useful for the field projects but won't impact EasyPower in any form. These have to be considered when we do harmonic study data collection. User will be responsible to follow the methods and entering the corresponding data into the EasyPower. What this slide means is that 519 in 2014 version has added quite a bit of requirements for the measurement devices in terms of the window of the measurement, accuracy classes, type of reading the data. All those things have been added. I mean, people who do a lot of data collection, I would assume they knew about it, but those who do more of an office work, maybe these are new. And again, it means that it actually says a lot about the importance of the data collection. As I said, for harmonic calculation, perhaps the study and study work is as important as collection of data. There are type of studies that I don't really want to make a comparison side by side, but when you do load flow studies or power flow studies, it's much more straightforward in terms of the data. It's like a kilowatt value, a kVAR value, power factor value, voltage value, all those values that you measure them once. If you do it correctly, that's it. For harmonics, you have to really make good assumptions at some point. I gave an example of just a few maybe minutes back that you get the data sheet from the turbine manufacturer or from a photovoltaic manufacturer or from a VFD manufacturer. You do the same measurement, you do the same type of test and measurement on your field, and your values are not entirely in line with the data sheet from the manufacturer. So that says a lot about this type of studies, that you have to be extremely careful and you have to be extremely knowledgeable and comfortable that the assumptions that you make, you would be able to explain it to other engineers, being your users, being your colleagues, being your higher management. You have to be able to explain that why did you choose the test data versus the data sheet from a manufacturer. And the calculations and all those things are rather more complex, let's say, versus load flow calculation. So that again brings us back to the point that it's not just EasyPower. You have to have the good knowledge, and then you have to put EasyPower in use for you to produce the good results. Otherwise, if you just make assumptions, if you just click a button and run EasyPower, it's not going to help a whole lot. But regardless, back to the 2014 version, there are a lot of updates in 2014 about the devices. It's for us, and as a software manufacturer, what we will consider is that you do a good job, you collect all those information and you put them in the software. We get it from that point. We do this simulation for you. The first point is that there are new voltage limit values. That's table 1, IEEE 519 2014 versus table 11.1, IEEE 519 1992. And I'll just show them in the standard, and we can just look at them here as screen captures that I got from the software. Table 1 adds a new voltage THD limit for phase voltages at PCC smaller than 1 kV. This is part of the new table in IEEE 2014. As you see, there is a category for voltages smaller than 1 kV, and individual harmonic are acceptable up to 5%. Total harmonic distortion can be up to 8%. That's IEEE 519 2014. Back here, this is table 11-1 voltage distortion limits. This is 1992 version. If you see, it does not categorize voltages lower than or less than 1 kV. So it goes 69 kV and below, and this is the limit. 69 kV to 161, and these are the limits, and 161 kV and above, and these are the limits. So high voltage systems can have up to 2% THD where the cause is an HVDC terminal. This is just a note. I'm gonna ignore it for now, but this is the equivalent table in 2014. Just compare them side by side. Let's just do it together. From 1 to 69, 3, 5, 3, 5, the same. 69 to 161, 1.5 to 2.5, 1.5 to 2.5. The same thing. 161 and above, 1, 1.5, 1, 1.5. Again, this category is new. It wasn't there, has been added, and has more tolerance. It's allowing the lower voltages and low voltage systems to have a little bit more tolerance for harmonics. You want to see that in the harmonic, in the standard itself. Here, this is the table 1 in IEEE 519 2014, and let's just go back, bring in 1992 version, and 1992, I believe it was here, this table, and I just discussed them. So these are the values. So this is first update, first change that I see in 2014 versus 1992 version. I'm gonna put this guy aside, move on to the next slide. Current distortion limits for systems from 120 volt to 161 kV have identical values. However, in 2014 version, second harmonic has been excluded from the table. All the new TDD limits for the current are limited to harmonic order 50. This, in fact, maybe I should have put this one first. Depending on what type of a study you do, it looks very important, but the impact of it is really minimal if you think about it. How many of systems or how many of, let's say, VFDs you have seen that they have a major harmonic contribution above 50th order? 50th order in a 60 Hertz system is going to be like 3000, like 3K Hertz. It's more like it becomes high frequency, more or less, at least to us as power engineers. I'm sure that it's for communication engineers might be in the lower bands, but for us as power engineers, it's really high. You don't see a whole lot of them, but now it has become a requirement. So what it says is that forget about anything beyond 50 Hertz. I'm sorry, forget about any harmonic higher than 50th order. Don't even consider it. We don't call it a harmonic order anymore. So that's what it says. And again, so this here, the first condition, it says that the current distortion limits for systems from 120 volt to 261 kV have identical values. However, in 2014 version, second harmonic has been excluded from the table. So let's just go here. Current distortion limits, table 10-3, obviously 1992 version. Current distortion limits for general distribution systems, 120 volt to 69 kV. Let's look at the values. Smaller than 11th order, between 11 and 17th order. That to me says 11, 10, 9, 8, 7, 6. It goes all the way down to the second harmonic. You don't see any exclusion of the second harmonic here, right? Right below is the table for IEEE 519 2014 version. Bunch of differences that if you don't pay attention, you may not be able to catch it, because if you just look at the values 20, 20, 20, 50, all look similar. And look at this column, 4, 7, 10, 12, identical. 2, 3, you can just check all of them one by one. They all are identical. The difference though is this one in 2014 specifically excludes the second harmonic. It doesn't even count it. It doesn't consider it. So it starts from the third, goes all the way to 11, while you here had it all the way to the second. So this is one change here. You go to the upper end of this frequency and you will see it says harmonics higher than 35. Higher than 35, the question would be how high you want to go really. And I come here and I think it's a more scientific, more realistic engineering definition that it really cuts it off at 50th order. And you go from 35 to 50th and that's it. You see the difference here. Even though the limits haven't changed, they are exactly the same limits if you just look at them here. So they haven't changed, but there are limits. Second harmonic was excluded, which is important. As we all know, second harmonic usually shouldn't exist in power systems. Even harmonics shouldn't exist in power systems. If there are second harmonics, there is a high likelihood that it's coming from an inrush current of a transformer. It should not be a sustainable event. It shouldn't be something that goes on for cycles and cycles. In fact, if it just dies down after a while, categorically, we don't consider it a harmonic. Harmonic is a waveform that sustains itself for a long period of time, something that doesn't go away. Something, so inrush current, even it introduces second harmonic, and even if you wanted to consider the second harmonic, basically it's not a harmonic issue. It's something, it's a transient issue. It's a different thing of different nature. And let's go back and just, you know, look these tables up. Let's start with 1992, that becomes table 2. That, I'm sorry, that becomes table 10-3 here. Next, next, and next, and next. Here you will see the same exact table here, all those values and a lot of notes. And I short circuit maximum short circuit at the point of common coupling, and I load maximum demand load here. And I'm gonna go here and look at the table. I forgot what table was it. Table 2. Here, as you see, second harmonic excluded. It goes all the way to 50 Hertz, 50th order, I'm sorry. Now, what would be the impact? Basically, let's just take a look at the impact of these changes. What would be the impact of these changes in terms of harmonic calculations? Let's say EasyPower engine currently does calculate all the harmonics all the way up to whatever you put in. So basically, if you go to EasyPower here and you define a harmonic source here, let's say this guy, and let me just go back, activate it. You go here, you go to harmonic sources, you define these values all the way up to 9, 11, 13, 15, and it goes all the way to 50, 53. You can do that, and the engine calculates it. Two ways. Number one, if you are using the current engine as we are updating it, we don't recommend you to go. I mean, you don't need. It's not a matter of recommendation. If you comply with 519, you don't need to go anything beyond 50th. That's number one. Number two is that if you have second harmonic, which I doubt, if you really have second harmonic in your system, there is, and it doesn't die away, there is an issue. There is a problem with your system. You have to look more carefully into that to see why there is an even harmonic in your system. But if obviously if you put it in here, the engine is gonna calculate it. It's not gonna exclude it. So now that being said, I come back here and let's take a look at the limits we discussed are the same. Let's take a look at the output for EasyPower. So let me just take a look. Let me just show you where you can see the 519 reports. If you want to see the 519 reports, you would go to harmonic options. You would go to text output and you would check this checkbox. So it generates for you IEEE 519 report. But if you do that, what you need to do is you have to go and define a breaker like this breaker, which is going to be your point of interconnection, because 519 is very clear, very specific about the fact that all those limits are going to be applied to the point of interconnection. You're more than welcome to use it and apply it to any other point in your system. That's not just compliance with the standard. That's your opinion. That's your engineering judgment. If you want to comply with the standard, you would just go and choose the point that your plant gets connected to the utility, and at that point you have to define monitor 519 point of common coupling. You would need to define these two values. EasyPower gets these two values from you, comes here, calculates from these tables, calculates these values, looks at this category, picks up the category, looks at the harmonic order, compares the available existing values with the limits. So that's what EasyPower will do. So you would know what's the importance of putting those values in EasyPower correctly. Okay, so that gives you the limits here. Now going back, let's just run the 519. Just I put numbers here. Let's put, I don't know, 1 2 3 4 5 2. Let's put 10,000 kVA. Let's put this one 25 and click OK. Harmonics, run it, look at the values. Okay, bus name POC, I checked it only for one bus and it starts giving me the values. Odd harmonics, existing value, IEEE limits. Even harmonics, existing values, IEEE limits. And these are the values that I just put in, and it just gives them to me. That's how it compares it against the harmonics value. So that's how engine, in fact, just for you, that's how our engine very much goes and provides you with a report. So this is a report, and obviously nothing is failing here. Everything is below IEEE limits, but I just put in some really random numbers. And I close this report. I go back to our presentation, and table 4, current distortion limits for systems rated at higher than 161 kV. And that what it says is that this is from IEEE distortion limits for 120 volt and 69. This is, so it goes all the way to 69. And then there is another table that you will find as table 4 in IEEE 519 2014 version, which goes for the voltages even up higher than 161 kV. And that's, again, you would see the same rules, goes all the way to 50 and excludes the second harmonic. So that has become like a general rule. Everything goes all the way up to 50th order, and second harmonic is excluded everywhere, and you would see that here. So that very much gives, even though I understand I kind of covered the really high level comparison of 519 2014 version versus 1992, but it gives you a really good understanding of what's going on. These are the major important values and tables that have been updated in 2014, and so that's how it's been done. If you run and perform the study in EasyPower, you should be aware of these changes. In the meanwhile, we are in the middle of updating on our own engine, and there is not a whole lot of really code changes. Some of the tables might need to be updated. Other than that, we're good. And if you know the limits, because these limits haven't changed, so your results and your harmonic studies shouldn't change much. But the purpose of the presentation really was just highlighting the differences, what has changed in 2014, and I hope that it's now clear for you guys. You can just use it in your studies and work with it. That being said, I wanted to conclude the presentation, which you hope that it's useful. You can use it in your work. If you have any question, please reach out to us. You can again send me an email at EasyPower, or just give me a call or get a hold of our technical support department, and technical support department, they will forward your questions to me. Thank you very much for listening and watching the webinar, and I hope that we come back with a new webinar soon, and I really look forward to hearing constructive inputs from you guys. Thank you and have a great day.